Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of pressure. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? And the question number four, how to learn the knowledge in this course. All right, so let me start with the answer to the first common question that you may have in mind, okay, which is about why to study this course. By now, you should know that our mission on Earth include, number one, to understand the world, number two, to improve or change the world. Then how to understand the world? The answer is to discover the knowledge in the physical world. Then how to discover knowledge in the physical world? The answer is to make you right? Then how to obtain sensory data? The answer is to make use of measurement and the sensing system. All right. Our second mission is to change or improve the world. Then how to improve the world? The answer is to invent smart machines, smart products, smart system. Then how to invent smart products, smart machines, smart system? The answer is to incorporate closed loop feedback control system inside these machine, product, or system, right? Then how to implement closed loop feedback control system? The answer is to incorporate sensory data, because sensory feedback is one of the three basic module or three basic building blocks inside a closed loop control system. Therefore, measurement and the sensing system is necessary for us to implement closed loop feedback control system. And in this slide, then you will see in future city, we need to have a smart parking system, smart light, smart street lighting system, smart building system, smart home system, smart environmental system, smart healthcare system, and also in future we may want to deploy Internet of Things in city area and in many other areas, right? So immediately you understand, okay? That this course is extremely important, not only for industry but also for society, right? The second common question that you may have in mind is about how to study this course. My recommendation to you is to put yourself into the mindset of a designer. Then with the keyword of the design or designer, automatically you will ask these four questions. Question number one, who are the user? Question number two, what are the needs from this user? Question number three, what are the functionality of the product or system that you are going to develop in order to meet the need of this user? And question number four, what should be the solution behind the design of your future product or system? All right. So answer to question number one is obvious to you now, because this user include ourselves, human being, and also include smart machines, smart products, smart system, right? Then what are the needs from this user? Their needs are quite similar because they want to have sensory data, right? Then what should be the functionality of your future product or future system which could meet the need of this user? So the answer depends on the specific nature of user. For example, a vehicle may need a certain type of a sensor, a robot may need another type of a sensor, all right? So that depends on the specific nature of a user. Then what should be the solution, or what should be the answer to question number 4? So the answer is to study this course. At the end of the study of this course, you will know the solution behind the design of your future product or future system, such as sensor measurement and the sensing system, Internet of a sensor or Internet of a sense, right? And the third common question that you may have in mind is about why you're going to study from this course. Basically, this course includes the study of physical principle behind the design of a popular sensor in electric domain, mechanical domain, environmental system, and the intelligence system. In addition, this course covers the basic detail about the physical world and the conceptual world. Also, this course covers the basic knowledge for you to cope with randomness in the physical world and for you to understand fuzziness in the conceptual world, right? Then the fourth common question that you may have in mind is about how to learn the knowledge from this course. Basically, you will learn the knowledge from this course to guide the design of sensor, Internet of sensor, or networking the sensor by following, the general guideline shown in this slide. Because the design of a sensor involves 2 steps, Step number 1 is to transform the value of a physical quantity under measurement into readable value. Step number 2 is to do calibration in order to produce the output, which will be exactly equal to the value of a physical quantity under measurement. In addition, the unit of a measurement assigned to the output will be exactly equal to the unit of a measurement of the physical quantity under measurement, right? Then for step number 1, you may face 2 situations. One corresponds to the case in which it is good enough for you to just use from-end sensing element to convert the value of a physical quantity under measurement into readable value. However, in most cases, you may face the second situation in which you have to make use of both front-end sensing element and back-end sensing element in order to convert the value of the physical quantity under measurement into readable value. All right, so this slide basically shows you the general guideline for you to apply, learn the knowledge. Now we are ready to study today's lecture, which is about the measurement of the pressure, all right? So pressure is a physical quantity related to force, like torque. Torque is also a physical quantity related to force. However, pressure is an independent physical quantity, all right? So you should not consider that the pressure depends on force, right? So for example, the pressure produced by gas is just proportional to temperature, proportional to volume, proportional to the molar number, etc. Then in that the equation of ideal gas, there's no presence of force, right? So later on we'll show you the equation. So pressure is an independent physical quantity which is directly related to force, right? Torque is also an independent physical quantity which is directly related to force, right? And in future, I believe the most popular application with the use of the pressure should be the smart shoe. Today's shoe is passive. The shoe does not provide feedback to human being about the pressure distribution, because the pressure distribution underneath our feet actually indicate our pattern of walking, and the pattern of walking may indicate the state of health All right. So I believe in future, if let's say all the shoe become a smart shoe, then constantly the shoe can communicate with our smart handphone. All right. And every day we know our pattern of working, then more or less we know our health condition. All right. So because every one of us need to wear shoes every day. All right. So this could be the most popular application in the world. All right. So as usual, so it is very important for us to have a quick overview or study. For those of you, if you can remember what you have learned from physics course in year 1, then you treat this first section as a revision. But for those of you, if you have already forgotten, okay, the physics behind the pressure, then you treat the section 1 as a quick study about the basic physics behind pressure, right? Then subsequently, our focus should be placed on the indirect measurement of the pressure and direct measurement of the pressure, right? So pressure is a very important physical quantity, and there are many applications involve the use of pressure, not only in industry, but also in society, all right? So this first video will show you the typical application with the use of pressure in industry. All right.
Applications of pressure in liquids. In a public water supply system, water from a river or a decameter is pumped to a water treatment plant. After treatment, the water is pumped up to a water storage tank, situated higher than all the house in that area. A water tank is usually built atop the roof of each house to store water and maintain constant water pressure. Due to the gravitational pull, water in the storage tank is maintained at a high pressure, and this enables water to flow to the houses of the consumers which are lower. A decameter is built across a river to collect water for the purposes of water supply, irrigation and generation of hydroelectric power. A thicker wall is required to withstand greater pressure, since water pressure increases with depth. A firefighter requires a fire hose for directing a water jet of very high pressure to put out fire in a high-rise building. To produce a pressurized water jet, the water is accelerated by an electric pump before flowing through the fire hose. A doctor uses a special mercury-filled manometer, called a sphygmomanometer, to measure the blood pressure of a patient. An inflatable cuff is placed around the upper arm of the patient, and air is pumped into the cuff until it squeezes the patient's arm to stop the blood flow in the arteries. On releasing the air in the cuff slowly, the doctor takes the maximum blood pressure reading. At the instant he hears the first sound of a spurt of blood. When the cuff pressure has fallen to the minimum blood pressure, the sound disappears. The doctor takes this reading as the minimum blood pressure reading. An IV injection is used for injecting solutions of salt or medicine into the vein of a patient. Solutions flowing from the IV bottle into the patient's vein is assisted by gravitational pull. The IV bottle should be suspended at the optimum height to ensure that the fluid gauge pressure of the IV bottle is greater than the pressure in the vein. Thank you for taking time to watch.
All right, so then this second video will show you application with the use of pressure in our daily life activity.
Applications of atmospheric pressure. The diagram shows a person drinking with the help of a straw. When air is sucked out from a drinking straw, the air pressure inside becomes lower. The higher atmospheric pressure, acting on the surface of the drink, pushes the drink into the drinking straw and enables it to be sucked into the mouth. A syringe consists of a tight feeding piston which moves in a cylinder with a nozzle at one end. When the nozzle is dipped into a liquid and the piston pulled up, the pressure below is reduced. The higher atmospheric pressure acting on the surface of the liquid pushes the liquid into the cylinder. When the piston is pushed down again, the liquid is ejected. A siphon consists of a rubber tube used to remove liquid from a tank. The rubber tube is filled with liquid, and one end is placed in the liquid container. When both ends of the tube are opened, liquid flowing out through one creates a partial vacuum inside the tube. At point S, the higher atmospheric pressure acting on the surface of the liquid pushes the liquid upwards into the rubber tube. The difference in air pressure produces a continuous flow through the rubber tube as long as the point Y is at a lower level than the liquid level in the tank. A rubber sucker is a rubber cup that can be made to stick onto a smooth wall such as glass or tiled wall. The rubber cup is made airtight by wetting its rim before pressing it against the wall to create a partial vacuum by driving the air out. The higher external atmospheric pressure outside presses down on the sucker and makes it stick firmly to the wall. A vacuum cleaner operates by applying atmospheric pressure to remove dust particles. When it is switched on, a fan sucks out a stream of air from the SpaceX to create a partial vacuum. The higher atmospheric pressure outside pushes the air and dust particles into the SpaceX. The dust particles are trapped in a dust bag at X, while the fast-moving air is allowed to flow out from the back of the vacuum cleaner. A lift pump is usually used to draw out liquids, such as kerosene from a tall tin or a tank. It consists of a barrel which has titrating piston, with a side tube near the top to act as a spout. There are two valves, A, fixed on the piston and B fixed at the bottom of the barrel. Both these valves open upwards. When the piston is pushed downwards, the valve B closes, and the valve A opens to allow air to move out through the piston. During the upstroke, A closes and the pressure inside the barrel is reduced due to the increase in volume of the air inside it. This causes the liquid to be pushed into the barrel by the atmospheric pressure acting on the liquid surface. On subsequent strokes, the liquid completely replaces the air in the barrel. After a few such strokes, the liquid will flow out of the spout. Thank you for taking.
All right. And then in development of a smart home system, and eventually we may want the floor in our let's say living room or dining room to have such a smart carpet, okay, and which will detect the movement of people inside the living room, etc. So this could be application inside the smart home system. All right.
Researchers at MIT's Computer Science and Artificial Intelligence Laboratory have developed a smart carpet capable of tracking human actions. The device's tactile sensors are capable of evaluating people's postures without using visual images from cameras. It's enough for a person to stand or sit on the carpet and perform an action, and the neural network with deep learning determines what exactly the person did. The engineers are confident that their invention will be useful for medical purposes, smart home systems, and computer games to track the physical activity of users. The relatively inexpensive technology is based on pressure-sensitive film and conductive filaments with 9,000 sensors, each one converting human pressure into an electronic signal that can be read as data.
All right, so you see, at the beginning I mentioned eventually, if let's say we have such a product called smart shoe, all right, because shoe should be more important to every person, all right, and then in this case, okay, we should be able to constantly monitor the health condition or working pattern of individual, especially for elderly person, all right. So now we are ready to know, okay, what is the pressure, all right? So by definition, pressure refers to force per unit area applied perpendicular to the surface of the object. And here object may refer to the sensing element. For example, we can place surface inside the gas, okay, or inside the container which contains the gas, etc., right? And over which the force is distributed, right? So mathematically, the definition is interpreted as a ratio between perpendicular force and the surface area. So we have a perpendicular force divided by the area, right? So then the unit of measurement is Newton per meter square. So this is the basic unit of measurement for pressure, right? And this unit of measurement is also called as a Pascal, right? And in practice, in industry, we may have heard of many other type of unit of measurement. For example, pound per unit or per square inch, something like that. And the bar, right, tall, etc. And in the video, you may have heard of this term, atmospheric pressure, right? So we may use atmospheric pressure as a reference, okay? Because at the sea level on Earth, there is a pressure. This is the pressure due to the air, the gas, all right? Then we may use that value to serve as a reference zero value. So because with that reference zero, it is easier or more intuitive for us to understand the meaning of the value, all right? Because later on we'll show you, we have this absolute reference zero, okay, for pressure, but that value, okay, is not so intuitive for layman to understand, okay, the value of the pressure, right? So then this table will help you to do the conversion. So you may heard of the unit of measurement such as a pound per square inch, and the bar, Pascal, and the ATM means atmospheric pressure, right? And we also have this technical atmospheric pressure, right? So AT, something like that. And the basic unit of a measurement, okay, in this case is 1 Newton per meter square, which is also called 1 Pa, okay? So Pascal, all right? Then what should be the conversion? The most important conversion for you to know is this conversion between the unit of measurement of Pascal and the unit of measurement of atmospheric pressure, because we use this one to serve as another reference zero, okay? So 1 atmospheric pressure is another reference, okay, for the measurement of pressure, right? So then it is very important for you to know this equality. So 1 atmospheric pressure is equal to, you see, 101.325 kilopascal. So that means the zero reference, okay, in terms of a unit of a measurement of Pascal, it is okay, it is far below, okay, 1 atmospheric pressure, because 1 atmospheric pressure is the pressure in the space in which we are living in. So we are used to it. Then this is a 100,000 value above, okay, the absolute zero reference. So then in the mind of a layman, it's difficult to do this conversion, John, right? So then for our daily life, it is easier to use ATM, because ATM means it is the pressure at the sea level on Earth. So it's easier for us to understand the meaning of the value, all right? So this is why, so for pressure, we have a 2 reference for zero, all right? One is the absolute zero in terms of Pascal, okay? Then another reference is the pressure at the sea level on Earth, all right? And because of the use of these 2 reference, then people may talk about the absolute pressure, gauge pressure, vacuum pressure, and etc. So this is why you need to pay attention, right? So you will see the conversion between the reference zero in terms of the ATM and the reference zero in terms of a Pascal is this value, okay? So 1 atmospheric pressure is equal to, you will see 101,325 Pascal, all right? So So this is the common practice, okay, or convention, okay, adopted by the international community. So we must follow this convention, all right? And because of these two reference zero, then we can talk about the absolute pressure. Then in this case, so we have a two chamber. For example, we want to measure pressure on the right-hand side. Then left-hand side, we have absolute zero pressure, okay, in terms of Pascal, all right? Then this reading should be the absolute pressure, all right? And if the inside here, the pressure is equal to 1 atm or atmospheric pressure, so that is reference zero in terms of atmospheric pressure, then the reading, okay, for this pressure on the measurement is called the gauge pressure, okay? When the gauge pressure is negative, then we call it as a vacuum pressure, right? And in other cases, we may want to measure the pressure difference at the two locations, P1, P2, then we call it as a differential pressure, right? Okay. And this slide help you to understand the difference between absolute pressure and the gauge pressure. For example, inside the tire of this motorcycle, the pressure is equal to 40 pounds per square inch. Convert it into Pascal is 275,790 Pascal, right? Then this means what? This is a gauge pressure, okay? So then you see this value is a gauge pressure, all right? Then what should be the absolute pressure inside the tire? Then you must add this value with this value, then you get this number, okay? So this is the absolute pressure inside the tire of this motorcycle, right? Then what is the concept of a vacuum pressure? Vacuum pressure basically means negative pressure relative to 1 atm. For example, inside here, the pressure is below 1 atmospheric pressure. Then in this case, the reading, for example, inside here is equal to 1,000 Pascal below, okay, below the atmospheric pressure, okay. Then what should be the absolute pressure inside the pipe here? Then the answer should be this we put is a negative value, like you see, 1 atmospheric pressure minus this one, okay. So 1 atmospheric pressure is equal to 101,325 Pascal minus 1,000 Pascal. Then we get this value. Okay, this should be the absolute pressure inside the pipe. All right, so this is just for you to know this terminology, all right? And then, okay, what is exactly the relationship between gauge pressure and the vacuum pressure? Okay, so here you see these two situations. So you remember gauge pressure basically is a differential pressure in which one pressure is equal to atmospheric pressure. Okay, so you can see this relationship. Okay, let's say in this case, if P1 is equal to P0, then this differential pressure is equal to gauge pressure. All right, so you know their relationship. Okay, so then in this case, if let's say now inside here is the pressure on the measurement. This is open to the air, so it is atmospheric pressure. Then in this case, you will see this pressure is higher because this pressure will push the liquid inside the tube up in the right-hand side. Okay, and in this case, the pressure is smaller than atmospheric pressure. Then in this case, atmospheric pressure will push the liquid up in the right-hand side, left-hand side. Okay. So then in this case, here we have a negative pressure, negative relative to 1 atm. It's not relative to absolute zero reference. Okay, pay attention. Negative pressure means negative with respect to 1 atm, right? So then we call this as a vacuum pressure, right? Since apply the force, you remember in the definition of the pressure, pressure is equal to apply the force per unit area, right? So apply the force could come from a solid, come from a liquid, come from the gas, all right? So therefore, the pressure could be produced by solid, liquid, and the gas, right? So then here, for example, water can be in one of these three states. Water could be in the state of ice, state of a solid, state of a liquid, state of a gas, like a vapor, water vapor, or steam or something like that. All right. Okay. So therefore, pressure could be produced by solid, liquid, gas. All right. So in this case, so this drawing showing you the pressure produced by solid. Okay. If the applied area is smaller, then pressure will be higher with the same amount of applied force. All right. And in this case, immediately you understand the pressure produced by liquid is a function of the depth inside the liquid. Okay. So deeper we goes higher the pressure. Then this is why when we have an outlet at the point D, then immediately the pressure at the point D is higher, then the water will come out at the higher initial velocity. Then this is why the travel distance in the horizontal direction will be longer than the travel distance by the water flow coming out from point A, okay? Because at the point A, the pressure is lower, right? So this helps you to understand the behavior, okay? And also the physical meaning behind okay, higher pressure, lower pressure, etc. And also the conversion from the pressure to force, force to acceleration, acceleration to initial velocity. All right, okay. Then for gas is the same, okay. So if inside a closed space, and if you have gas inside, then this gas will have pressure P1. And if you have another type of a gas, then you have a P2. And here it is interesting for you to know this Dalton's law, okay. When we put these two together, so actually the pressure is the sum of individual pressure, right? The final pressure is equal to P1 plus P2, okay? So this is an interesting result for you to know, right? So then this slide basically illustrates, okay, the pressure produced by gas, because inside the gas we have a particle, okay? And then inside the closed space, then there is a pressure. And if we just approximatively consider the gas is ideal gas, then we can use this ideal gas equation for us to understand, okay, the relationship among the related physical quantity. For example, for ideal gas, the pressure is proportional to temperature, inversely proportional to the volume of a closed space, and proportional to the molar number. Molar number basically is an indication about the amount of mass, okay, of the gas inside the closed space. R is a coefficient, okay. So depends on the unit of a measurement of pressure. If the pressure use the unit of a measurement of kilopascal, then R equal to this value. If P make use of unit of a measurement of atmospheric pressure, ATM, then R equal to this value, okay? So R is a constant coefficient, all right, okay? So, and in the open space, you can always imagine that we have this column of air, okay? So this column of air has a mass then act on the surface at this level, okay? Then we can talk about what should be the applied force per unit area, all right? So in the open space, so we just imagine, okay, we have a column of air, and this column of air has a weight, all right? Okay. Then in closed space, then we treat as an ideal gas, okay, or approximatively, okay, as an ideal gas, right? And then based on the equation of ideal gas, then we can study the situation in which the constant, the volume is a constant. For example, in this closed space, and the volume never change. We only change the temperature by adding thermal energy. Now here you see the thermal energy appear. Heat means what is the thermal energy, all right? So then the temperature will change then there is a relationship between pressure inside the closed space and the temperature. Then this table showing you the relationship between pressure and the temperature. When temperature increase, pressure increase. And here you will see for temperature, temperature is another independent physical quantity, which also has a two reference for zero. So it's like a pressure. Pressure has a two reference for zero, right? One is absolute zero in terms of the Pascal. Another is at the sea level, is use ATM, use the pressure at the sea level to serve as a reference, all right? So ATM. So, and then for temperature, we also have absolute zero, okay, in terms of Kelvin, okay? Then we also has another temperature in which water will become, will make a transition from liquid to solid, okay? So that temperature is called as a 0 degree Celsius, all right? So you see, we have two reference for zero, all right? So this is why, so we have temperature in terms of Celsius, temperature in terms of Kelvin, all right? Okay. And then this example showing you the scenario in which temperature is constant, okay? So we, okay, top up the thermal energy in order to maintain the temperature remain as a constant. Then in this case, then you see relationship between pressure and the volume. So when volume decrease, then the pressure will increase. When volume increase, the pressure will decrease. So this just for you to know, okay? The equation of ideal gas, okay, which relate pressure to temperature to volume, all right? And for gas, it is important for you to know this Dalton's rule, okay? For example, we have a gas A, B, C. If we add them together, then the pressure of the final mixture is equal to the sum of the pressure PA plus PB plus PC, right? So it's quite straightforward. Then second situation correspond to the pressure produced by liquid. Then in this case, we can imagine we have this column of a fluid, and the fluid has a weight, okay? Then this weight divided by the contact area, then will give us the value of the pressure produced by the liquid, all right? So the weight is equal to mass times gravitational acceleration. Then the mass is equal to density of the fluid times the volume. Then the volume of the fluid is equal to area times the height, all right? So it's A times H. Then A cancel out, then you see this equation, density times height times G, all right? So this is a pressure, okay? We can also call it as a hydrostatic pressure inside the fluid or liquid, all right? And here the H refer to the vertical depth inside the fluid, all right? And this example showing you that at the same okay depths, okay, vertical depths inside the fluid system, the pressure should be the same. So this is the same fluid system, okay, within the same fluid system at the same vertical depths, okay, the pressure at the point ABC will be the same, all right? So this is a background knowledge for you to know. And this is another background knowledge for you to know, okay, inside a fluid system at the steady state, okay, steady state means there's no more turbulence inside the fluid system, okay, when the fluid system reach the steady state, then at any two location or any point, okay, inside the fluid system, there is a conservation of this sum, right? So pressure plus density times height times G plus 1/2 density times velocity square equal to constant, right? Then how to memorize this formula? So actually you can just imagine this is equivalent to work done by applied force. This is equivalent to potential energy. This is equivalent to kinetic energy, because you look at the equation, quite similar, all right? Then you can say the sum of work done by force, potential energy, and kinetic energy is conserved. So because you add them this together, this is more or less correspond to mechanic energy, because mechanic energy include work done by force, potential energy, kinetic energy. Okay, so you just imagine this is more or less like energy conservation. All right, okay. And we will study the fluid system in separate lecture, right? So here, so I just show you this background knowledge about the Bernoulli's equation, all right? Okay. And case 3 is a familiar one to all of us, because our body is a rigid body. Okay, we can push something, we can pull something, and we walk on the surface of the land. So actually, when we walk on the ground and constantly we exert, okay, pressure on the ground, and the ground constantly receive pressure, okay, from our body, okay. So that means constantly we produce pressure, all right, as a rigid object, all right. So then this is a scenario showing you pressure is being produced by solid. Then in this case, then the force come from the wheel, okay. Then in this case, force come from applied force, all right. So it's quite straightforward. So that's about the basic physics behind pressure, okay. Now our major focus should be on the indirect measurement of pressure and the direct measurement of pressure. So indirect measurement means if we know the value of a related quantity, how to calculate the pressure, okay, without doing direct measurement, right? And however, so you understand, for this course, the focus is to study the principle behind the design of a measurement and the sensing system, right? So let's first look at the way how to calculate pressure, okay, from knowledge of related physical quantity, right? And this is the first example, okay? So in this case, we will see we use this U tube, okay, to serve as a manual measurement instrument, right? So then in this case, the pressure of the gas is below atmospheric pressure. Then this is a negative value with respect, if we use a unit of measurement of ATM. So with respect to ATM, so the pressure value is negative, okay? So it means this value is a negative, right? Or in this case, then in this case, the pressure inside this closed space is higher than atmospheric pressure. So then you will see we have this scenario. The level of liquid in the right-hand side is higher than the level of liquid in the left-hand side. Then in this case, the level of the liquid in the right-hand side is lower than the level of liquid in the left-hand side, all right? So then we'll get the negative value for this term. Here we'll get the positive value for this term. So it's quite straightforward, all right? So as long as we know the density of this liquid inside the U tube, then we should be able to calculate, okay? The gauge pressure, okay? And then how to compute differential pressure. Then in this case, okay, so here is input of a pressure P1, this is input of a pressure P2. Now we want to know the difference between P1, P2. Then again, this difference is equal to this term, all right? And this term is proportional to the density of the liquid inside the tube, and also the level difference, okay, between the left level and the right level inside the U tube, right? And then, okay, so this is a detailed example, okay? So these are the background knowledge for you to know how to apply, okay, the equation, okay, to calculate, okay, the differential pressure and the calculate the gauge pressure, etc. Right? So for example, now in this case, we have this pressure on the measurement, and this is a positive pressure, okay, with respect to the reference in terms of ATM, okay, because this side is open to the atmosphere, right? So then this level is higher than this level, the H is positive. Then in this case, so we should be able to calculate the gauge pressure as well as absolute pressure. P is absolute pressure. This term is a gauge pressure, right? So then this is atmospheric pressure, okay? So atmospheric pressure is equal to this one, all right? Then this one equal to density times G times H. Density correspond to the density of a mercury, because inside here is a mercury, all right? So question tell you the value. Then pay attention to the unit of measurement. You must make use of a basic unit of measurement. Remember to do the conversion. G will be converted into kilogram, and the centimeter will be converted into meter, all right? So G is a gravitational acceleration. H is the difference between the level. So it's a 10 millimeter. Convert this one into meter, right? So this is the conversion after conversion into meter. So this is the level difference. Then you get these two values. So this is the gauge pressure. Then add them together will give you absolute pressure. Okay, so it's quite straightforward. And then in this situation, so inside the pipe, okay, so we have a section with a normal diameter. Then we have a section with a smaller diameter. Then if you apply this equation of conservation of volume, okay, then immediately understand the flow rate or flow velocity at here will be higher than the flow velocity here, all right? Then when you have a lower velocity, then you will have a higher pressure. This is another background knowledge. Higher the velocity, lower the pressure, right? And the higher velocity, then the pressure here will be low, and the lower velocity will be higher pressure, then the pressure here will be high. So this is why then you see this difference in the level, okay, inside the U tube, right? So then what will be the gauge pressure? So gauge pressure is equal to density times G times the level difference, right? So you put in the value, and then you should be able to get this answer. So pay attention to the conversion of a unit of measurement. So gram must be converted into kilogram, centimeter must be converted into meter, right? So something like that. Then here we want you to calculate the pressure inside the tire, and assume the tire has a 5 liter of air, and mole number is 0.225 mole, all right? So this is the volume of a tire, all right? And the temperature inside the tire is 30 degrees Celsius. But pay attention, because in a separate lecture, we will study the measurement of temperature. By now, you just need to know that the Celsius is one reference for 0, and the Kelvin is the absolute, is a reference for absolute 0. And here we must use absolute temperature instead of relative temperature, okay, with respect to this unit of measurement, all right? So we apply equation of ideal gas, okay? Pressure is proportional to molar number, temperature, and volume, okay? Temperature should be equal to 30 degrees plus this offset, okay? Between the reference 0 in terms of Celsius and the reference 0 in terms of Kelvin. Because in this slide, basically showing you this offset already. Here, you see, the 0 reference in terms of Celsius is equal to 273 degrees in terms of Kelvin. So this is the offset, okay, between reference 0 in Celsius and the reference 0 in Kelvin, okay? So this is the value, okay, for us to do the conversion, all right? So then, okay, 273 plus 30 degrees Celsius, all right? Then, and we know because here we want to use ATM because, okay, so we just calculate the gauge. So this is this will be the gauge pressure, right? Because because this is a closed, this is not open to the air, otherwise all the air will exit from the tire, all right? So then the measurement is basically is a gauge pressure, right? So this is a gauge pressure. Then we use this unit of measurement. Then the pressure, okay, value, we'll have ATM as a unit of measurement. If you choose another coefficient with respect, in which we will make use of Pascal as a unit of a measurement of the pressure, then here will be Pascal, right? Okay, so this is background knowledge for you to pay attention to know also, all right? Then how's about the solid? Okay, so in this case, let's say we can place a book on the table in this way and also in this way. Then in this case, what should be the pressure difference? All right. So in case one, so the weight of the book is equal to, okay, here we already tell you the weight. Okay, we did not tell you the mass. Okay, so it's 11.1 kilonewton. Okay, so the weight is the same. Now we need to know what is the contact area between the book and the table. So in this case, it's 20 cm times 50 cm. Okay, we must do the conversion, make use of meter as a basic unit of measurement. In the second case, the contact area is equal to 100 cm times 50 cm. Okay, then you get this value. So then you will see in this case, the pressure is lower, even with the same weight or with the same amount of applied force, okay? Because the contact area in case 2 is larger than the area in case 1, all right? Okay, then here's one more example for us to calculate the pressure produced by solid, all right? Then we have an elephant. The elephant stand in this configuration. That means 2 feet on the ground, 2 feet in the sky or in air, all right? Then the mass of the elephant is 500 kg, and the area underneath each foot is 100 centimeters square. Then what should be the pressure, okay, produced by this elephant in this configuration, in this posture, all right? Okay, so it's a weight divided by area. The area is 2 times the area of a single foot, all right? So you get this number, okay? Quite straightforward, all right? Okay. Then our major focus of this lecture is on the direct measurement, because this course is about the measurement and the sensing system. Then what should be the physical principle for us to apply in order to guide the design of measurement and the sensing system for pressure, right? So, and then you may want to know, why do we need to design measurement and the sensing system for pressure? Why do we need to have a pressure sensor? So at the beginning, I already mentioned to you, maybe in future, the most popular application with the use of pressure could be smart shoe, because every one of us need to wear shoe every day, John, right? So this could be one of the most popular, okay, application with the use of the pressure, okay? So this is a typical scenario, okay? If let's say inside our shoe, we should be able to output this matrix of pressure value, okay? Then we know the distribution of the pressure. Then eventually we can calculate what is the center of the pressure during our walking, okay? Then the shape of that center basically reflect maybe the change of the physical condition about the person, okay? And eventually by monitoring this center of the pressure underneath each foot, and eventually we may, okay, monitor the health condition and of the physical body of that person, all right? So I believe in future, this could be the most popular application, okay? So in practice, we can make use of these two principles to guide the design of measurement and the sensor system for pressure, okay? The first principle is to convert pressure into voltage by making use of piezoelectric material, all right? And since we know that the all microcontroller are programmable sensor of voltage, therefore the principle number 1 should be quite straightforward for us to follow, all right? Then, however, we can also apply this second principle, which transform pressure into the variation of resistance. And we know that we are able to convert resistance into voltage, all right? And of course, mustn't prevent you to apply other principles such as convert the pressure into variation of capacitance or inductance, etc. All right. So I guess these two principles should be quite simple for us to implement. All right. So and here you must pay attention that we need to measure, let's say, absolute pressure, gauge pressure, or differential pressure, right? For differential pressure, then you see this scenario like P1, P2. We have there's a tube just to pick up P1, another tube to pick up P2, then and direct them into left chamber, right chamber. These two chambers are being separated by diaphragm. Okay, then the diaphragm will undergo displacement or will pick up the force or net force due to the difference of these two pressure. Then in this case, basically we have a pressure just come out from the applied force, right? So we need to know whether we need to measure, okay, the differential pressure, absolute pressure, gauge pressure, okay. However, mathematically, all this measurement can follow this scheme because when P0 or P1 is equal to P0, so then this is a measurement of gauge pressure. That's it. All right. So when P1 is equal to absolute 0, okay, then this is the output of absolute pressure. All right. So okay. So you know the relationship among these three types of pressure. All right. So now we want to know how to apply principle 1 to design measurement and the sensing system for pressure. Then in this case, the principle is very simple. Okay, first we convert pressure into voltage. Then we use a microcontroller to convert voltage or DC voltage into a digital value, which are readable by human being and also readable by computer. All right. By now you should know that okay, all microcontrollers are programmable digital sensor of a voltage because inside all microcontroller we have a digital counter which could do the prediction about the digital value. We also have a voltage synthesizer inside all microcontroller which will predict digital number into analog, okay, DC. Then all microcontroller has this comparator, okay, between two analog voltage in the input. So this is a predict DC voltage. This is the input DC voltage. When these two DC voltage equal to each other, then this module will issue a signal to stop the prediction. Then the value inside digital counter is the output of digital value. So this digital value is computer readable and also human readable. All right. So I guess every one of you know that, okay, this module inside every microcontroller, right? Then our job is just to add in this extra module, which will do pressure to voltage conversion. That's it, okay? Then what should be the extra module for us to add in? The answer is to, the simplest answer is to make use of a piezoelectric material, right? And this video show you the response from piezoelectric material, all right? And this demonstration will convince you about the performance with the use of piezoelectric material. Then you see when there's apply the force, apply the pressure, then voltage come out, then voltage will produce electricity, and this electricity should be strong enough to drive photodiode. Okay, so the diode will light up, right? And by now, okay, you may ask this question. Okay, so in the design of force sensor, we make use of a piezoelectric material. In the design of a accelerometer or acceleration sensor, we also make use of piezoelectric material. Now, in the design of a pressure sensor, we also make use of piezoelectric material. Then what are the difference among these three sensors? So, and this slide basically help you to understand the difference. Okay, for the measurement of force, then you will see the input is applied force. For the measurement of acceleration, the input to this piezoelectric material is induced force by acceleration. And this induced force is called inertial force, picked up by inertial mass. All right. So these two types of force are different. All right. So you understand? So try not to confuse between inertial force induced by acceleration on inertial mass and externally applied force. Okay, from external object onto receiving object. All right. Then for the pressure sensor, so basically we do implicit conversion from pressure into the force, then force applied to the piezoelectric material. So you see the slight difference among the design of these three type of sensor. Okay, so this comparison will help you to have a better understanding about the design of acceleration sensor, design of a force sensor, design of a pressure sensor with the use of piezoelectric material, right? And here showing you one more example of making use of a piezoelectric material to guide the design of a pressure sensor. So you will see the pressure on the measurement is here, and it comes in on the diaphragm, and the diaphragm basically will convert pressure into force, then force applied on the piezoelectric material such as a crystal or quartz crystal. All right, then output will be the voltage, right, or DC voltage. All right, okay. Then how to apply principle 2 to guide the design of a measurement and the sensing system for pressure. Then in this case, we need to have two extra modules. One is to do conversion from pressure to resistance, and the second one is to do conversion from resistance to voltage, right? And by now, okay, we know that there are plenty solution for us to do conversion from pressure to resistance. Okay, so here I'm going to sharing you some, okay, typical design or innovative design for you to follow. Okay, for example, this is the pressure on the measurement, and we have this chamber, and on top we have this diaphragm. Then on top of the diaphragm, if you look at the top view, then we place 4 strain gauge in this specific way. Then you will see R1, R2, okay, is in the radial direction, and R1, R3 are in the radial direction, and R2, R4 are in the tangential direction. So therefore, R1, R3 will receive radial stress, and the R2, R4 will receive a tangential stress. All right. So when pressure appears, so then the diaphragm will expand, and this expansion will produce a larger expansion on R1, R3, smaller expansion on R2, R4. If we construct this circuit is a Priest circuit, then you will see R1, R3 is in this direction, R2, R4 in this direction. All right. So when R3 increase largely together with R1, the variation of R3 is larger than variation of R4. So that means the voltage drop at this point will be bigger than the voltage drop at this point. All right. So then, and again, when the variation of R1 is bigger than variation of R4, actually this voltage at this point will increase. Okay, and another way to understand, okay, you see variation of R3 is larger than variation of R2, then voltage drop at this point. Okay, voltage at this point will drop. Okay, because this one has a larger increment, this one smaller increment, then therefore there is a decrease in voltage at this point. Then for the lower branch, because variation of R4 is smaller than variation of R1, then voltage at this point will increase. So this one decrease, this one increase, then you will see actually the amplify the voltage difference between these 2 points. Right, so this is a quite innovative design, right? And the second solution for you to do the conversion, okay, from pressure to resistance is by following this design. For example, apply the pressure will make the diaphragm to undergo deformation. This deformation could be converted into linear motion. Then this linear motion will drive or move the viper of a potentiometer, right? Then resistance value will change. All right, so this is another solution for you to consider. And this is one more solution for you to consider. So now in this case, we have 2 barrel, left barrel, right barrel. Then we have a P1 enter the left barrel, P2 enter the right barrel. In this case, P1 could be 0, could be P0. That means atmospheric pressure, all right? Or P1 could be just absolute 0, okay, pressure, right? So then the pressure difference will produce a net force acting on this vertical beam, okay? And the vertical beam will deform either toward the left-hand side or right-hand side, all right? Then on the beam, we have R1, R2, R3, R4. So you will see R1, R3 will expand or contract together, okay? When the beam bends toward the left-hand side, then there's a contraction, a compression, okay? R1, R3 will be compressed all together, okay? Then R4, R2 will be expand all together. So then you see we form this pre-circuit, okay? So when R3, okay, increase, then R2 will reduce, then this one will drop, okay? And when R3 increase, R2, R4 will reduce, then R1 will increase, then this voltage will increase. So that means the voltage difference actually will be amplified, okay? The effect is a double effect, okay, due to the variation of resistance, all right? So this is also quite innovative design for you to consider, right? And of course, we may have other solution. For example, we may have a matrix of a sensing cell, and inside each sensing cell, we may place R1, R2, R3, R4, 3 strain gauge inside this sensing cell. So when there's an external applied force, okay, placed on top of this surface, then the resistance value of these 4 strain gauge will change, right? Then based on the change of the strain gauge value, we should be able to calculate what should be the pressure, okay, for this area, because each cell has an area channel, okay? So then the voltage, okay, should be related to the pressure applied to this cell. Then for each cell, we can have a reading. Then result is what? A matrix of pressure. Then based on this matrix of pressure, then we can calculate what is the distribution of center of the pressure. And that distribution basically indicate the working pattern of the person, and also may indicate the health condition of the physical body of that person, right? So this could be a guideline for you to come out the design of a smart shoe with the capability of monitoring the center of the pressure, okay, during the working by a person, all right? And besides these two principles of design for the measurement and sensor system, okay, there are other design principles. For example, we can convert the pressure into linear displacement of a spring. All right. So and eventually you can measure elastic force. For example, you place a strain gauge here and piezoelectric material here. Then because when the spring compressed, okay, then you can pick up the voltage. And also you can, okay, we follow this principle of the pressure will produce linear motion. Then in this case, the pressure will produce angular motion. All right. So in practice, there are many principles for you to follow. All right. So after the design of step 1 inside your measurement and the sensing system, always remember to do calibration. All right, because previous slide basically tell you how to obtain value yi from input xi. Then by doing calibration, we will produce zi, and the zi will be exactly equal to xi. In addition, the unit of a measurement assigned to zi is equal to the unit of a measurement of xi. Okay, and we want the relationship between zi and xi follow this straight line, which is 45 degrees above the horizontal line. All right, so remember to do calibration, and also remember to do error analysis. So it means after the fabrication of your sensor or sensing system, okay, then you can use your measurement and the sensing system to do experiment, okay, repeatedly to do the measurement. Then in this case, you can calculate mean value, standard deviation. You can also increase the input and reduce the input, then collect the data, then to do the comparison, whether, okay, with sample or recorded the data, okay, from the value when the input is increasing, okay, and compare the result with the data, okay, when the input is decreasing, then to see whether there's a gap or not. If there's a gap, that means there's a hysteresis error. All right, so these are the extra work you need to do, okay, because the buyer of your measurement and sensing system or user of your measurement and sensing system may want to know this information. All right. So that's all for the study of this lecture on measurement of pressure. All right. So key takeaway from this lecture is for you to understand the basic physics behind this physical quantity pressure, and also we have studied the way to do indirect measurement, and in particular we have studied 2 useful principle which will guide you to undertake the design of a measurement and the sensing system for pressure. All right, thank you for your attention, and I'm looking forward to seeing you in the study of next lecture.